Hello, everybody. My name is Matt Taylor, and I work for Numenta. I've worked there for about 5 years. So one thing I want to say before I start is this is awesome that there's so many people talking about biologically inspired intelligence at this conference this year, because last year I think I was the only person. So I'm very excited to talk to you about this. Let me share my screen and get to some slides here. I'm going to talk about the biological path towards strong AI. And this is a talk about brain theory for the most part. I'm the open source community manager for Numenta, and I'm also an engineer. So in summary, I'm going to talk about intelligence in a broad general term and define the difference between weak and strong intelligence. Then we're going to dive into some minor brain science, after which I'll introduce hierarchical temporal memory, which is really the technology that I'm pitching in this talk. And I'll talk about the fundamental aspects of that theory of intelligence, including the medium of information, which is sparse distributed representations, or SDRs. And then I'll talk about some specific algorithms in HTM, data encoding, spatial pooling, and temporal memory. So way back in the beginning of 2015, I saw this Wired article, and in the title of it, it said, AI has arrived. And I remember being upset about this because I was like, I don't agree that AI has arrived. And it made me realize that I have a different definition of intelligence than a lot of people in the community do. So maybe if I modify this to say weak AI has arrived, I think I can agree with that statement. But weak AI, the type of AI we have now, can do some really amazing things. It's huge right now. Everybody needs AI. Everybody wants it. You know, the artificial neural network inspired technologies of today and all the different directions that it's gone can do amazing things. So this is in no way putting down what we can do right now with weak AI, because I think it's really important. But my point is, by my definition of intelligence, what we have today is not intelligent. So what would I say is intelligent? Well, that falls under the term strong AI or true AI. Some people call it artificial general intelligence. And Wikipedia says the requirements for strong AI is the ability to reason, use strategy, solve puzzles, represent knowledge, plan, learn, communicate in natural language. And the kicker, the last one, integrate all these skills towards common goals. Now, that's a huge deal because we might be able to, with weak AI, put together specific systems that do some of these things, but integrating them together into a system that can do amazing things is really hard. I'm going to take this one step further and say that what we have today is not strong AI, but also weak AI won't produce intelligent systems. There are others at this conference that are sort of echoing this sentiment too, of some of the presentations I've watched. So if it won't produce intelligence, then why not? What's missing? So I'm going to tell you what's missing. The very first thing is realistic neurons. The artificial neural network neuron that was created decades ago was the best we could do with what we knew about neuroscience at the time. But it was a very simplistic model of a neuron. And based upon that really simple model of a neuron, we've done some really amazing things. So imagine if we went back, now that we know so much more about neuroscience and about how neurons interact with each other, especially in the neocortex and other parts of the brain, what we could do with that if we tried to implement new intelligent systems with this more biologically realistic neuron model. So I think this is a big part of why we won't get strong AI from today's artificial neural networks. Another thing that's moving, that's missing, if you're talking about intelligence, is movement. This is a key thing. Everything that's intelligent today, that's alive today and intelligent, has to move and explore its environment in order to learn how its actions affect its environment. All of the AI systems, the weak AI systems that we have, don't have this integration of movement into their systems. They are generally being fed data and taking action upon that data, but they don't have the ability to explore that data. If you're a data scientist, maybe you understand how a human could explore a complex data set. So we need systems that have the ability to do those explorations on their own cognition. So our mission at Numenta, and we've been around for over a decade now, and this has not changed. Our mission is to understand how intelligence works in the mammalian neocortex and create software based on those principles. And the reason is because we think that to create intelligence, we need to study what we know is intelligent today, and that is brains. So let's talk about brains. So this is a picture of your brain. The wrinkly thing is the neocortex. If you were to spread this neocortex out and flatten it, it's about the size and shape of a dinner napkin. And it's completely homogeneous for the most part throughout. So if you took a slice of the neocortex from your visual processing area versus your audio processing area versus your motor generation area, whatever, it's going to look the same under a microscope. The cellular structure of that layer of cortex is homogeneous. What that means is that the same algorithm is operating everywhere throughout the cortex, no matter what it's processing, no matter what motor commands it's generating. It's the same algorithm. And this is very encouraging because it sort of tells us that if we can crack this set of algorithms that are running in a small section of cortex, that could go a long way in understanding how intelligence works. So that's what we work on at Numenta. So let's say we have a model of a bunch of neurons in a section of cortex. Our point is that we're going to model each one of those neurons as realistically as possible, and its interactions with all of its neighboring neurons as realistically as possible. And there's some key differences between our neuron model versus the older ANN models. One big one is that a neuron can get input in different ways. It can get proximal input, which is a feed-forward input from some input space that it really doesn't know much about. And it can also get distal input, or lateral connections that spread throughout the structure and connect to other neurons in the same structure. And I'm going to talk a little bit more about this too. So this is, what I'm talking about is hierarchical temporal memory. And it's an evolving theory of intelligence based upon this neuron model that I'm trying to explain to you as biologically plausible as I can. I'm going to talk first about sparse distributed representations. So you can think about this, the way I like to think about it is like a fiber optics cable. And every one of those fibers in that cable is like a bit. And whether it's on or not means something. So if you think about a nerve bundle as a fiber optics cable, and each one of those, whether the nerve is active or not, representing some semantic meaning, this is what a section of cortex might be fed forward. This might be the proximal input for a section of cortex. So it's looking at this space that has a sparse activation, so generally 2% activations, and it's trying to derive meaning from it as it's changing over time. So I'm going to show you some visualizations of sparse distributed representations. So here's an example. This is just a 2048-bit binary array, essentially. I've got 40 bits on. I can change this if I want to, but I'm going to keep it at 40 because that's 2%, and that's the typical sparsity of the brain. And the point I want to make here is that the amount of representations that you can show in this space is astronomically large. There are more ways that you can put 40 bits in this space than there are atoms in the known universe. So there's not going to be a problem of running out of room to represent things in this space. And this is just 2048 bits. So that's one key point about sparse distributed representations. The other one is, I want to talk about this one. So imagine here's one sparse distributed representation. In this one, I've got it just as an array. I don't have it, wrapping around. The other one, I just wrapped it around. So I'm going to make these big SDRs. So now they're 2048. This one is 2048, but it just continues onward like in this direction. I'm just not showing it. Now I'm going to add a bunch of these to the stack. So now I've got, I don't know, 50 SDRs in the stack. Let's add another 50. So now we've got 100 SDR. There we go. 100 SDRs in the stack. So I'm going to show you some comparison operations here that are important when we talk HTM theory. So I'm going to take one of these SDRs. I'm just going to grab one randomly. I'm clicking it, and this is going to apply 25% noise to that SDR, and then show it up here with 25% noise, and then match it based on how much it overlaps, how much of its on bits overlap with every other SDR down here. And we can tell with 25% noise, there are 30 bits that still overlap out of the 40. Obviously, we put 25% noise, so 10 of those are off. But we can still easily identify, and this is a comparison of I've stack ranked all of these SDRs, and I can easily identify this one, even with 25% noise. Let's bump it up to 55% noise. Again, I can manage the threshold so that I can very easily identify this is the SDR, even with 50% noise. So even with noise involved, and let me show you, I can also give you exactly what the false positive possibility is going to be. So with this SDR with 68% noise, I can match it within this group of 100 with a false positive probability of 5 or 6 times 10 to the negative 12. So it's still pretty good. So the point here is SDRs are very noise tolerant. They're also very fault tolerant, but I'm going to skip that part of the demonstration. So let me see if there's any questions. Got lost with the SDR stuff. So at the end of this presentation, I'm going to show you some resources so that you can watch some videos about all this at your own speed. And it goes into much more detail about SDRs, much more detail. So you'll have some resources to do that. But the point here is that the communications medium of the brain is SDRs. Let me try and explain this a little better. If I'm a neuron, I have all these connections to other neurons. They might be proximal connections, which are feed-forward inputs from some space, or they could be distal connections, which are looking at other neurons like neighbors nearby. Each one of these is an SDR. So a neuron's view of the other neurons that it sees is an SDR, and at any point in time, generally 2% of them are on. Those all mean something. So the neurons it's connected to are telling it something about the current state of whatever's being observed at the time. So that's how SDRs work in the brain. You can look at it from a neuron standpoint. All right, I need to get back to the slides because I have a lot to go through. So after SDRs, we have to talk about encoders. So here's one of the problems that we face with HTM is how do we get our data into this SDR format? So that an HTM system can understand it, because you have to convert it into this bit array. And encoders are basically equivalent to your senses. Your retina, your cochlea, those are extremely complex encoders. Those things have had millions and millions of years to evolve. So we don't have software encoders with that complexity because it's still hard to understand how those systems even work. But we do have some very simple encoders, which I'm going to show you. Oh, I should have made that full screen, but so I'm going to show you an example of a date encoder. So here's an example of me taking some data, which is a date, like this is today, and encoding it in a way that the semantics of today, the date that right now is being encoded. So I can encode the day of week here. I can encode whether it's a weekend or not. I can encode a general sense of the time of day, and this isn't exactly the time of day, it's a general sense of it, and the same thing, a sense of the season. So as I walk through this, I go to tomorrow, Monday, Tuesday, Wednesday, you can see the day of week encoding changes. It has a different encoding for every day of the week. When we go from Friday to Saturday, the weekend encoding changes. So that represents that we're in a weekend versus a weekday. And then as we continue to bump through, you can see going through June, July, the season encoding isn't changing. It's changing to represent a season change. I can also change the time of day, and that affects the time of day encoding. You might also notice that all of these encodings are simply concatenated together to give you an entire encoding that represents all of these semantic details of the timestamp, including day of week, which I think is one of these is buckets is day of week, one is weekend, one is time of day, one is season. And as we go through it and you look at that representation, you can see those things changing in different ways as I, whoops, sorry. Okay, so that's one way of encoding data. We also have other encoders. We have scalar encoders that can encode numeric data, but I'm not going to get into that right now. I'll give you a short example. Let's talk about an input space. So here's an example of a real piece of data being encoded into an input space. So you can think of this SDR at the bottom left as sort of that nerve axon that's feeding into a cortical section. The cortical material has to try and understand the patterns in this data over time. So what I'm encoding in it is a scalar value, which is power. That's what's charted here. The time of day that reading was taken and whether it's a weekend or not. So as I walk through here slowly, you can see how the encoding changes over time. So we're dealing with a temporal sequence here, we're dealing with a temporal sequence here, not something spatial. I mean, it's a spatial temporal representation, but it's changing over time, and that's key. That's the way your brain processes information. It needs to have data over time to understand it. So this is one way that I might encode this specific graph into an SDR. There's hundreds of ways I might decide to encode it using different mechanisms. So for example, there's another type of scalar encoder called the random distributed scalar encoder. I could use that, and that displays the semantics just the same as the other one, which was just a block of buckets. This one distributes, Jesus. So my point is there's lots of different ways you might encode data. This is a space in HTM theory that I think is ripe for different people creating different encoders for different things. I think it's a very cool aspect of the technology. Let's see here. I'm going to talk about spatial pooling now. So this is a bit, this gets a little tricky, but I'm going to do it anyway. All right, spatial pooling. So this is a core aspect of HTM technology. And so basically there are problems with this input space that we're talking about. If we're talking about this encoding, or this input space that has an encoding in it that's coming from some encoder, and every bit has some semantic meaning. The problems are we don't have control over the sparsity of that input. So we need to create, and this is what the brain does, this is a discovery, not an invention. The brain needs to normalize that representation somehow, and it does this by doing a process called spatial pooling. In a cortical layer of the cortex, there are these structures called mini columns. That's what you're seeing on the left here in a drawing by a famous neuroscientist. Each one of these mini columns can have many cells in it, many neurons in it, and they all share the same proximal connection to that input space. So I'm going to talk a bit about that. These are feed-forward input coming from some input space that could represent sensory information, or perhaps information from other parts of the brain as well. So as these mini columns are observing that input space, they become active over time. And this allows us to normalize the sparsity of encoded representations while maintaining the semantic meaning. And that's the tricky bit. So I'm going to, you guys can still see my screen, I hope. Going to talk about, what was it? Connected synapses. So this is, just want to make sure you guys can hear me. Yeah, great. So here's the input space on the left. Doesn't have anything in it. I could show the input. This is just an example of some input that might be in it, but I don't care about that. I just want to show you the relationship that the spatial poolers mini columns have to the input space. So on the left are just bits coming from some encoding. On the right is the neocortical structure that we're building, seen from the top. So we're looking at the top of these mini columns. Each one of these boxes contains one or many neurons, and we're going to have to talk about that when we talk about sequence memory. But for right now, my point is each one of these mini columns has a different relationship with the input space. Let me click on one and you can see this column that I just clicked has these connections to the input space. When the spatial pooler initializes itself, it sort of pseudo-randomly connects to the input space so that it has a place to start with. So these are all connections. Every one of these columns has a different set of initial connections to the input space, okay? Something to make this a little more complicated is it's not just whether it's connected or not. Each one of these columns has a very specific relationship with each cell. So in this case, this cell, there is a permanence value between every column and every bit in the input space. So over here on the right, you'll see this the permanence value displayed here, and this is a connection threshold. These are all configurable values. So as I look at this bit right here, it's connected because its permanence value is high enough, it's over the connection threshold. This one also is over the connection threshold, so it has a blue dot. This one is not, it's too low. So this is just the initial state of the spatial pooler. as the spatial pooler learns, let me talk about learning. As it sees information, so here's an example. I'm going to turn this mouse highlight thing off. So here's an example of one input, and I can see every column's relationship to that input. Okay, so here's the first column. It is not an active column because the amount of bits that it has overlapping with the current input is not high enough for it to become activated. However, these green ones have enough bits or connections that overlap with the input space that it has activated. So this is how the spatial pooler now can represent the semantics of the data within a fixed sparsity over here on the right, while still maintaining what each bit means. And there's, let's see. Yeah, so there's sort of a competition over here for at each time step, which columns become activated based on the spatial input. And you can sort of see this competition in a simple fashion over here. We just stack rank them by their overlap score with the input based on their connections to the input space and the on bits in the input space. The ones that overlap the most, we're going to activate somehow. And all these parameters are tunable, so you can really kind of focus it on based on what your data looks like. Okay. Let's see. So temporal memory. So spatial pooling, like just to reemphasize, gives us a space for a sequence memory algorithm to operate within. So in my last little drawing, I drew mini columns in yellow. These again are mini columns, but I'm not looking at the proximal feed forward input. I'm looking at distal connections. This is the different type of neural connection. So within each of those mini columns, each cell can form connections to other cells in any other part of the structure. These connections help identify the context of the input based upon what it's seen in the past. And all of this works within the mini columns that the spatial pooler has sort of established with its mapping to the input space. And what the temporal memory does, the algorithm does, is it puts cells into a predictive state if a certain amount of their connections have on bits on the other side. And just to reemphasize, here's the biological neuron that I showed earlier when I compared it to ANN. This is an HTM neuron from our theory. This feed forward is the proximal input. That's what I was talking about with the spatial pooler. That's from the encoding space, the input space. And all of these are distal segments that this neuron has with other neurons in the same structure. So as it's getting these feed forward inputs and columns activate, the cells inside of those columns decide whether they're going to be active next based on its connections to other cells in the structure. So let's go to my big visualization now. Okay, this is the sequencer. So I'm going to need to spend a little time setting this up, okay, just so you understand what's going on. Can you hear those notes? It's coming out of my computer. So this animation may not come across beautifully, but this is what we've got. Make sure you guys can see it. So over here, I've got a note sequencer, basically. And we're just going from C sharp, E, F sharp, C sharp, just one after the other. This sequence starts fresh every time. And at the end of the sequence, I'm cutting it off. So every time we see the sequence, we know it's a new sequence. Here is the encoding space. This is the input space. You can see the different encoded representations for each of those notes. There's also representations we're not seeing here for A and for arrest. This represents the active columns right now, and you can see, you know, these are columns. Let me spread this out a little bit, and you can really see those columns. Okay. So this is the spatial pooler in action right now, activating columns based on the input. So let me show you the proximal connections. I'm going to select a column like this one, so you can see exactly what input bits that column is connected to, which is different from this column and different from this column. Some of these columns are never active because they never have enough overlap with the input space to ever become active. And also, this is a very simple pattern, so we're not going to be utilizing the capacity of the structure either. But there you can see the proximal inputs, okay? Now, I'm going to try and explain to you how sequence memory works within this structure that spatial pooling provides for us. So let me just pause on E, okay? So, well, let's go to the very beginning of the sequence. So this is C#. This spatial representation, this set of active columns represents C#. So what we want to do is activate neurons within these active columns to help to give this spatial representation some temporal context, okay? And there's two ways that the temporal memory algorithm does this. One is if we look through here, I'm going to show predictive cells, which will show nothing here, but you'll understand this in just a minute. If we look through every active column and there are no predictive cells, cells that have been put into a predictive state by their distal context, then we're going to activate all of them. So that's what happens here. Now I'm showing you the active cells. The yellow means that the column is active. The orange means that the cell itself is active. And as I step forward, well, I'll show you why. So in this case, because this is we've seen C# before, but we've never seen it within the context of another note because it's always the first note in the sequence. Okay, I'm doing sort of an artificial reset at the end of this sequence and starting over. Now, if we move forward one, now we're going to see individual cells in each column activate. Okay. And that's because the other thing that the temporal memory algorithm does is when it looks through the active columns to decide whether to activate the cell, first of all, if there are no predictive cells, it activates them all. This indicates the start of a sequence. This indicates something new just happened. This may be a branch off a current sequence or a new sequence or something like that. If there are predictive cells or cells in a predictive state like this, then it will activate only them. So in this case, we do have predictive cells here, and it activates just those predictive cells, okay? Now, the next big question is, how do those cells become predictive, right? Okay, so let me turn on the cells that are currently in a predictive state based upon these cell activations, okay? So how we identify this is by looking at each of these neurons. Let me see if I can click that one. And I'm going to show its distal connections. Hopefully you guys can see this. But this neuron right here has this one distal connection that is connected to all of these other neurons that are active right now. The reason it's active is because all these other neurons it's connected to are active. So basically, what this neuron represents is a prediction of F# coming after E. These active bits represent E coming after C#. And these predictive bits represent F# coming after C. So, and I'm going to show you something interesting here. I'm going to let this run for a little bit, and we're going to show you how sequences can sort of branch. So we're learning this pattern over and over: C#, E, F#, C#, over and over and over. And it's got enough that if I show you the correct predictions, these green ones means it's correctly predicting. So it's got this pretty much down pat. Every time it's correctly predicting the next note. And by the way, this is an extremely trivial example. I just did it for the sake of education. So let's stop at this E and take away the F# and play an A. So at this point, if we look at the cells that are currently predicted, what note are these cells predicting? Well, they're all predicting F# because that's all it's seen follow E in the past. So when we move forward and we don't get an F#, what's going to happen? I will show you what happens. Columns burst. This is called bursting when you have, and the reason is, if I go and show the predictive cells, all these predictive cells are predicting F#. So they were all wrong. But instead, we get this spatial representation in the spatial pooler, which we've never seen before. So in this case, this is when the temporal memory algorithm activates all of the cells within each of those columns, because it's like, this is a new pattern. I've seen C#E before, but I've never seen C#EA. So this is called bursting. Each of those columns will burst, and that allows the algorithm to kick off a new sequence from that point. And if I continue to run this now with this new pattern, C#EA, C# over and over and over, we'll see something interesting happen. Let me show the predictive cells. After it learns this for a little bit, we're going to get a branch in the sequence. So here's our E, we're back at E. And remember, we've now got two transitions from C#E to F#, which we learned first, and now C#E to A. So we've got twice as many predicted cells, because half of these are predicting F#, half of them are predicting A. And if we move forward, and let me show you correct and wrong predictions, we move forward, you can see that half of these red ones, were incorrectly predicted. Let me turn these off. And the other half, the green ones, were correctly predicted. So we now have this representation of the sequence with a branch in it. And as we continue to play through, the more it sees this second version of the sequence, the stronger it's going to reinforce that that's the sequence that it should predict whenever it sees E. And eventually, and here we are at eventually, it now is predicting A. If I were to switch this back and let it run for a little while, you'll see incorrect predictions, the red blocks, red, some red. But over time, depending on some of the parameter values and configuration values to set up with your neurons, we can increment and decrement those distal connections either very strongly or very weakly, so we can have it learn very quickly or very slowly. So now looks like it's still predicting A, but sometimes it takes a while to unlearn a sequence that it's already learned. But like I said, all that stuff is tunable. It's all tunable. Okay, so I'm gonna go, that was my last, uh-oh, we're all good? Okay, so that was my last visualization, and I'm going to try and finish up my presentation, and then I will go through and take questions. So just a note here, these are just the foundational components of HTM, or neocortically inspired intelligence. We're working on a lot more stuff. I mentioned movement as one of the requirements for strong AI. That's currently a big research area for us. I posted a talk, or a series of talks in chat earlier, where I talked to our founder, Jeff, about his thoughts on all that type of theory for sensory motor inference. So that's really important, and I think this next sort of evolution of algorithms that come from this research is going to produce a lot more capabilities for HTM. I also mentioned that I have a video series with all these visualizations that I'm showing you came from this video series. It's called HTM School. You can Google it. It should be the first thing that pops up. So I've gone through all of this in pretty extensive detail in this video series. So if you want to learn more about this, you can do it at your own pace. Just walk through these. I go through lots of stuff about SDRs, spatial pooling, and I just did a temporal memory episode a couple months ago. I'm working on the second one. It's just that one's hard. So to kind of sum up, all this stuff is open source. It's all on GitHub. You can see all the details about our community at Numenta.org. We've got a really great community, about 1,000 people or so on our forums, and everybody loves to help each other out. So and the community is interesting. Let me just put my contact info up, matt@numenta.org. And then I'm just going to talk to you. Let's do this. Okay. But the community is really great, because sometimes I have difficulties understanding parts of HTM theory, and I could post a question on the forums, and there's enough smart people on the forums that really do understand this stuff that they can help me out, which is nice. So we get community contributions to the theory, as well as community contributions to our code bases. We're constantly trying to improve this. I'm working on a 1.0 version of our core implementation of HTM. All of these visualizations were run on a system called NuPIC, which is the Numenta platform for intelligent computing. So as you saw those, that was a real HTM system running the theory that I talked about live on my laptop. Okay, so I'm going to try and get to some questions. Okay, so which visualization what was I talking about when you missed something? Because I'd be happy to go back. I think I have 4 minutes, right? Encoders. Okay. Oh, the date encoding thing. Okay, let me do that real quick. Entire screen, date encoding. So here is the date encoder. Okay, so I'll run through this. So all the semantics meaning day of week, weekend, time of day, and season, are all being encoded in an encoding down here on the bottom left. They're just concatenated together. So this is how we get the semantic meaning of a timestamp into an encoding that we can also add like other information, like scalar information. So we not only get the encoding of the scalar data, but also the time at which it was collected or time at which it occurred. That was really the main thing for encoders. And then I think I also talked about an input space. Did you guys see this visualization? This is a real data stream and encoded in how we might encode it in a real system. So this is one way of encoding it. We've got the scalar value sort of on the top moving up and down, and the time information semantics at the bottom. And I wanted to point out that there's other ways we can encode this. So this is the same semantic information being encoded in a different way. There could be hundreds of ways to encode this data. It's a big area of exploration, I think, in HTM that we can use. Oh, again, I think it's because I keep getting this thing to share. Here's the encoding. Okay, so here, day of week, weekend. I'm just moving through a calendar so you can see exactly what the encoding, how the encodings are changing, and in the entire encoding, they're changed there too. And here is the input space one that I was showing you. So this is a graph of scalar data and the subsequent encoding that is created. And if I can encode it in a different way like this with the exact same semantics being encoding, but just the buckets sort of distributed through the space. So there's tons of different ways you might do these encodings. That was my point. These aren't Python notebooks. These are, this is all very customized code that I wrote. But if you go to the HTM School videos, there's links to it. Yeah, the sharing option was kind of a bummer. Yeah, there are applications of this in production. Somebody posted Grok Stream. That runs off of our technology directly. I mean, it runs the NuPIT code base. Cortical IO is a partner of ours, and they're working on natural language processing using HTM theory stuff. They're focused a lot on SDRs, so they'll create fingerprints of words in SDRs. So you can get like an SDR for cat or dog and compare them to see how close they are. They're doing some really cool stuff. So I'm just going to try and address some questions before my time runs out. Sorry about the slide problem. Why simulate the human brain? Okay, so the bird versus the plane problem, yeah. There's a ton of stuff going on in the brain that we can learn from. And just in the same way that we didn't build, flapping planes, we might not model all the things that we see in the cortex, but if we can understand how it works, we should be able to implement it somehow, because we don't have anything close today to intelligence. So why not study something that we know is intelligent and try and figure out how it works? We're not trying to exactly replicate the brain. We're not trying to build a brain. We're trying to understand how it works and build software like the brain. The data does have to be temporal. You can use images, but they have to be a temporal stream of images. So here's a thought experiment. You can do feature extraction using deep learning technologies like weak AI technologies. So you can have a video stream, and if you process each image in the video, extract features from it, and then use those features to create SDRs. And then you can start to predict what features will be in the next frames of the video. All right, so I'm still here. I can hang out for questions if anybody wants to ask more questions. Go to numenta.org, get onto our forums. I'm very active on the forums. Okay, so the reaction time of a biological neuron is 2 to 3 milliseconds. Let's probably throw my hands because it. I have no idea how that's possible. So it's probably that. So one of the things we've learned about the brain is that your representation of, say, a glass or something doesn't exist in this particular part of your brain. It exists in the entirety of your brain. Like there's neurons representing this glass all over your cortex. Yeah, and I have to go because I do have a one-on-one booked, so I will have to go. But the point being that at the very lowest levels that react immediately, and a lot of this is talking about reflexes. We're not talking about reflexes. The neocortex is not involved in some of those lower level things like reflexes. Yeah, so I've got to go and do a couple interviews. So thank you all for watching. I really appreciate it. And go to numenta.com to learn more.